The idea of my talk is to talk about how we can use high-throughput computing to discover new materials. And I'll just jump directly into the outline. I'll start by talking about what materials discovery is all about and how the type of computation I do, ab initio computation, play a role into materials discovery. And then I'll jump into doing this basically, those type of computation hundreds of times or thousands of times, which is high-throughput computing with an example of transparent conducting oxides. And one of the issues we have is that we would like also to find entirely new phases, entirely new crystal structures, entirely new chemistries. And this is I'm going to tackle that problem here, hopefully if I have time to talk about how we can combine machine learning and data mining to achieve this. And finally, I'm going to talk a lot about generating data and looking at this data, but it would be nice to be able to actually disseminate this data to a wide audience of scientists, and this is the last part of my talk. Okay, so new materials are really important for many new technologies. I mean, if you think about an airplane, I mean, you can make better airplanes if you manage to actually bring carbon fibers that will make your airplane lighter. This is actually happening in new Boeing airplanes. You can think about producing energy and using a new solar absorber, and there's a really hype into this type of hybrid perovskites, which are really new type of crystal structure, of actually materials that you try to integrate to make better solar panels. And finally, I think you all heard about the Tesla, also not only about the materials, but also about what Elon Musk does. But the Tesla is based on battery technologies, and battery technologies really rely on material science problems. So basically, materials are really important for technologies. And so the tool I use to understand and try to predict material is called ab initio, or first principle computation. And the idea is very simple. We basically have all the very basic laws of physics to actually compute materials properties at the atomistic level. You basically need to solve the Schrödinger equation. And this is the Schrödinger equation for one electron. And actually, if you think about any molecule or any material, you can write the Schrödinger equation of this molecule, of this material. And this is a one-line equation. It might be difficult to understand, but it's really easy to write. And it's always something that amazed me, but any molecule, any material in the world can be described by this equation. So why is it so difficult? It's very interesting to see that Paul Dirac, very early on when quantum mechanics was built, actually said something very, I would say, very visionary at the time. He said that basically the fundamental laws necessary for the mathematical treatment of a large part of physics and the whole of chemistry. So that's the arrogance of the physicist, I would guess, because basically he didn't make a lot of chemist friends when he said that. Basically everything's known. But this is what's visionary from him. The difficulty lies only in the fact that application of this law leads to equations that are too complex to be solved. And early on in the 30s, Dirac was actually saying that the future of ab initio computation will be about how do we solve that very complex equation. And so what we do is we develop approximations to solve that equation. And one of the most successful approximations is called density functional theory. And maybe you've heard about DFT. And I don't have time to go in details about DFT, but the idea is very simple. You have a series of, the problem of the Schrödinger equation is the interaction of the electrons. So why don't we replace that interacting electrons problem by a non-interacting electron problem? That's easy to solve. Then you can tell me, but that's silly. I mean, electrons interact. But instead of that, you put them in an average potential that kind of makes every electron feels the interaction of the other ones. And the trick of DFT is doing that in a very efficient way to pick actually a good average potential that works quite well. And so this is a very, very important development. And actually in 1998, Walter Kohn received the Nobel Prize because of DFT. So this has really been impacting material science and chemistry a lot. And when DFT came along, people used it to understand a lot, to understand materials, and that's really very useful. But I'm going to ask now, can we actually predict materials properties, even before they've been characterized through a computer? And let me pick one example. for my own research. It's on solid-state electrolytes for lithium-ion battery. A lithium-ion battery, very quickly, is based on 3 components: a cathode, an electrolyte, and an anode. And I'm going to focus on the electrolyte here. And the electrolyte that you have a lithium-ion battery in your smartphone, it's based on an organic electrolyte. And this is the most common electrolyte. It's very good, makes lithium diffuse very fast, that's what you want, and blocks electrons. But the problem with this organic is that they're flammable, okay? And so this is actually the picture of a battery after a fire, and this battery was actually in a Dreamliner, the airplane. And that caused a lot of problems. So if you want to solve that problem of safety of batteries, one way of doing that is to actually develop solids instead of liquids. But you want to keep a solid that has lithium diffusion as fast as a liquid. And you can imagine that's a challenge. Lithiums are mobile in a solid as much as in a liquid. And so this is the challenge, and can we use DFT, ab initio computation, to help doing that? And this is a material we recently worked on, which is lithium titanium thiophosphate. This is not an obvious material for high lithium diffusion. And what we did is we simulated how the lithium would move. This is actually a movie of lithium moving at a very high temperature. And you see, actually, this has been computed through solving quantum mechanics and Schrödinger equation. Okay? You see it moves a lot, but that's not very quantitative. From that, you can extract actually a diffusion coefficient. And you like to compare the diffusion coefficient to something. So let's compute it, let's compare this diffusion coefficient of this new material to the diffusion coefficient with temperature of LGPS. What is LGPS? I'm not going to go in detail, but LGPS, I would say, is the champion of solid-state electrolyte now. This is the fastest material that's known so far. This is the best current technology. So how does this new material compare to? When we started running those computations, we found the diffusion coefficient, this diffusion coefficient versus temperature, that is way higher than the best. So if you're way higher than your champion, then you're really excited. And then you actually go trying to convince an experimentalist to confirm that prediction. This is a prediction from the theory. And so when we went, actually made this material with colleagues, and so we tested and measured the diffusion. This is again diffusion coefficient with temperature now measured. LGPS, remember, this is the champion. This is the organic liquids. I put them there. They're faster, have better diffuser. That's not a surprise. But then this is our material. LTPS is doing an order of magnitude roughly better than LGPS. And this is something that we confirmed experimentally, but it was purely driven by theory, by prediction by theory. So I hope with that I give you a sense that predictions can start to be made, really exciting predictions in silico, in the computer, even before the experiment. Okay, so this is the part on what's ab initio computation, what is materials discovery. But now I'm going to talk about how we actually scale up to, I would say, a high throughput level. And when you think about the many material science discovery process, a lot of trial and error. And maybe one of the most extreme example of that is when Edison looks for the best bulk lamp filament. What I've read is that his team tried around 30,000 materials. His team made 3,000 different bulk lamps. I mean, you can imagine that's a lot of work. And then you just pick the best. Okay. But I just told you that density functional theory is awesome, that we can use computers, that it's somehow predictive. So can we take the same approach, but with a computer? What if you had a computer? Can we speed up that process? And let's stay humble. Maybe you don't want to find the best material directly, but if you can, just lower that number from 3,000 to maybe a few hundred, I would argue that's already a big step, purely computational. And so this is the ambition of high-throughput computing. And usually you start with a database of compounds. There can be known, and I will talk about unknown compounds too. But most of the time, you don't know much about properties of compounds. And this can be of the order of 100,000, let's say, compounds and materials. And what you do is you start computing properties. And by definition, we always face multi-property problems. So you never have one property. You often want to optimize several properties. And then, I mean, depending on the problem, those properties will be here. And I put here a funnel. And why do I put a funnel? Because unfortunately, I talked about approximation. All properties don't have the same cost. All properties, some properties need a lot of computation. Some properties don't need much computation. And so what we do is we put the easy properties first. And with that, we already remove the most uninteresting candidates. Let's say you want to find a solar absorber, and you find a material that's transparent. Not very interesting to absorb light. So you can remove that material. And as you go down and you screen out materials that are not interesting, you get less and less candidates. And there I would say you can come with the big guns and use much higher order methods to compute, approximations that are more expensive, or properties that are by definition more expensive. And so down there, what we hope doing is to reduce the number of possibilities. At the end, when you've done this tiered screening, you actually end up with not 100,000 possibilities, but maybe 10 to 100. And there you work with the experimentalists to actually confirm these materials. Okay, so I want to talk about three very big challenges in doing that. And this is relevance, accuracy, and infrastructure. And the first one is sometimes a little bit overlooked. We should always remember that we're doing atomistic level computation. So I end up with things like band structures, I will get to that, density, energies. But often the problem you're facing are more engineering based. You want better safety, a higher hardness, better durability. And so that link is very important to be able to do. So we need to understand a lot about materials if you want to do this type of approach. And I would argue you need to work with experts that know how to link those two parameters. Sometimes it's possible, sometimes it's not possible. It really depends on the problem. So that's something we always need to keep in mind. Another one that is also often a concern, but I would argue it's less of a concern, is accuracy. Of course, I'm using approximation. I said that at the beginning. DFT is an approximation. So it's not 100% accurate. And so people are concerned about that. There's good reason to be concerned. But I would argue that I can work with a method that's not 100% accurate as soon as I know how inaccurate I am. So we can make decisions if we know the error bar. And that's very important. And there's more and more work in actually developing those error bars. And this is something that's going to be more and more important in the field if we want to be more predictive. One example, here we compare band gaps with different techniques. Band gap is a very important materials property. And different techniques, I mean, this is DFT, and this is a more advanced technique. And we can see, at least with this type of study, we can see how good we are. Statistically, how bad a technique is compared to another one. And finally, I will talk about the scaling up issues. I mean, for an engineer, it's very important. We all know scaling up is not always easy. Okay? And we do have that with computation, too. And when you work with one or two materials that you run computation on, the DFT computation, people running DFT computation know that there's some babysitting to do. You have to look if the computation converged, if it didn't fail, the computer crashed, or you changed some parameter. All these things you do, it's okay if you have one or two. Okay, like it's okay to babysit one or two babies. But we want to do high-throughput computing. So what are you going to do if you're going to have to babysit 10,000 computations? And so this is a big challenge. We spend actually a good amount of time, I would say, in infrastructure. And every time you come with new properties, you have to develop the infrastructure around to do it not one time, two times, but 10,000 times and have reliable results. And so I'm involved in several efforts doing that, and often it's open source tools with a community working on the problem, which is very nice. And I can mention too Pymagen and Fireworks. Show this type of open source tools. Okay, so I talked about a few of the challenges, and I stayed quite general so far. But let's talk about an example, and that might be more concrete. And the example I picked is transparent conducting oxides. Okay, so transparent conducting materials. Why do we need this? There are actually many applications where you need a transparent and conducting material. And as you have a battery in your pocket, you also have a transparent conducting material in your pocket if you have a smartphone. Because your touch screen is actually based on a layer of transparent conducting material. This is one application. Solar cells need transparent conducting material also. And it's a really cool problem for material scientists, but usually transparent material are not very conductive. Think about glass. And, you know, conductive material are not very transparent. Think about metals. So combining that together is not that easy. But before I talk about how we combine that, let's do a very brief refreshing of what the band structure is. Because this is what we're going to analyze band structures of materials to find if they can be good transparent conducting material. Okay? So I'm going to go even further, and I'm going to say, let's revise chemistry, general chemistry class of, if you think about how hydrogen molecules form, okay? They have, you put the hydrogen together, you can have hydrogen atoms, 1s orbitals, they're in the fundamental state. And what they're going to form, what you've been taught in chemistry, is that you can have a bonding and an anti-bonding orbital, okay? So that's plus, minus, plus 1s, plus 1s. And this is what the little graph I really put there is related to the wave function, something very important in quantum mechanics. So this is a plus-plus wave function, this is a plus-minus wave function, this is a bonding, this is an anti-bonding, okay? And when you have this, you can, this is the last step, which is you say you have 2 electrons, so you put them both in the bonding state, and you know the hydrogen molecule is stable. Great. Okay? So what's the link with the solid? Let's take a hydrogen linear chain now. That's the simplest model of a crystalline solid I can have. What happens then? Do you have also bonding and anti-bonding? You have something that looks like this. You have also plus, solutions, but you also have plus, minus. But you have plenty of other ones. Intermediate, I would say, solutions, because you know you have an infinite chain. So you have a lot of different energies. Here you had 2. You have a lot of a continuum of energies. Okay? And so when let's look even further than that. And if you look at this like you're doing signal processing or something, you see that this is plus, minus, plus, minus, okay? Makes you think about something. Maybe it's like a modulation with some sinusoidal here. And actually, that's what it is. And there's a theorem called the Bloch theorem that actually exactly tell you that all the solutions will have a different wavelength, a different wave vector. Wave vector is 1 over the wavelength. A different modulation for all these solutions. That's called the Bloch theorem. And what's the link with band structure? No, every state that you can have in your solid can be described by this K vector, okay? So now I can show K, energy versus K. And that's really described my solid. And that's what the band structure is. So if you see this type of plots with K and energy, this is what it is. And each of these K is a certain modulation, and each modulation has a different energy. Okay? As for the H2 molecule, we can also fill the states with the electrons we have, and then we can count the electrons we have per hydrogen, and then you have a certain level you fill, and that's called the Fermi level. Okay? So this is filled here. So that's really band structure 101. You can generalize that to 3D. But this, it's just more complicated. Now you have a vector of K instead of a number, but this is the same idea. You can use Bloch theorem, and you have the same situation. And this is silicon, probably the most common and known semiconductor. This is the band structure in 3 dimensions of silicon. Okay? This is along certain path in the reciprocal space. This makes things a little more complicated, but you can think this is the same idea. And you have also occupied levels and the Fermi level. Okay, what can we learn from band structures? We can learn if a material is a metal or an insulator or semiconductor. And that's pretty easy. Let's look at the metal band structure. That's aluminum. Okay, you can see there's no state that is here. The really characteristic of insulators is that you have a certain range of energy where it's forbidden to be. Okay. Here you don't have this. This is a metal. Okay. Insulator or semiconductor, let's take gallium phosphide. This is the band structure of gallium phosphide. You have this band gap, this energy range where you cannot be. This is very important because this is driving electronic properties. Because the electrons here basically can move freely, it's a good electrical conductor. These tend to be poor electrical conductors, insulator or semiconductors, okay? But is it really given that they're not going to conduct electricity? Silicon can actually conduct electricity, but you need to do a trick. And the trick is to do doping. Doping is add a little bit of impurity to actually move this Fermi level, that's the last occupied state. And either you move it n, okay, you move this Fermi level a little bit, and this actually makes conductivity possible, or you move it p, and makes it also conductivity possible, either by electrons or by the absence of electrons that we call holes. Okay? And this doping thing this is how the semiconductor industry works, actually, through doping of semiconductor. I'll just optical properties are also linked to the band structure. This is the typical band structure of a semiconductor. You have the valence band that's filled with electron, conduction band that's empty, and if you shine light on that, and you change the frequency of your light, the energy of your light, it's only at a certain point that you will start absorbing. Only if you have enough energy to jump to that band gap. And so you can have this type of behavior. And this is really important. One of the things you can see is the color of materials. If I take gallium phosphide, the band gap is around 2.2 eV. I mean, visible light stops at 3 eV, roughly. So if you 2.2 eV, then it makes a material that absorbs light. And so you have this color. Calcium fluoride has a band gap of 12 eV. That's huge. It's a totally transparent material. So band structure can give you a sense of electronic properties and also optical properties. So they're very useful for this problem of transparent conducting material, because we want something that's transparent, so optical properties, and conductive electronic properties. So now that you know everything about band structures, what do we need for transparent conducting material, and especially a transparent conducting oxide? What people have done is they've taken a very wide band gap material, higher than 3 eV. That gives you transparency in the visible. Every photon will just go through this material. And then, that doesn't give you any electronic property, any electronic conductivity, sorry. So how do you do electronic conductivity? Then you dope, okay? And I really mentioned that you can do that for semiconductors, like silicon. You actually can do that with oxides with large band gaps also. And then you get a transparent conducting material. So you can be N-type, electron doping, or P-type, where the carriers are holes. Okay? So this is the way people have been doing that, and the material you do have in your pocket now, it's probably indium oxide doped with tin, or ITO. This is N-type material. This is really produced by tons. This is a very widely used material. So they work, those TCOs. However, the P-type TCOs, the one with holes conducting, they're actually not commercialized. And why is it so? One of the things that's really important is how mobile your charges are. And this is the difference in mobility, an order of magnitude between the best P-type TCOs and the best N-type TCOs. And this is why you don't have P-type TCOs in any application, because basically their performances are not as good. Why do you care? There's certain application, for instance, transparent electronics, where you want P-type, but also N-type regions. So basically, this has stopped this development of transparent electronics because of the absence of a P-type transparent conducting oxide. Okay. So let's go a little further to link conductivity with this band structure. And this is conductivity, and this is linked to the amount of carriers. That's going to be related to doping. Okay, how much you dope, how much impurities you can put. And then there's also mobility, how mobile those species are, or when those carriers are, sorry. And this mobility, you can relate it to something that's called a scattering time. That's how long an electron can live without being scattered by something, like a phonon, for instance, a vibration. But also by what's called the effective mass. And the effective mass is basically the mass of the electron just because it's in the crystal. And what's the link between this effective mass and the band structure? It's actually just a second derivative. So if I have a band structure, I can get an effective mass. and I can have a sense of mobility. Okay? So this is a very important factor driving mobility. So this is a light effective, and this is curvature, basically. This is a light effective mass, very curvy, and this is a heavy effective mass, very flat. Okay? If you want high mobility, you want the red one, not the green one. Okay? So if you look at getting back to this orbital picture, and if you wonder why p-type TCO are so bad in mobility, it's because usually an oxide looks like this in band structure. A flat valence band and a more curvy conduction band. Why is it so? You can actually find that the orbitals making this conduction band are usually based on the metal layer and based on the oxygen layer. And the oxygen orbitals are just more localized, and if you're more localized, you actually have a flatter band and heavier bands. You can think about being localized as being a problem for transport, and being delocalized being very good for transport of electrons. Okay? And so fundamentally, it's difficult to find a high mobility oxide for p-type because this band is usually flat. But still, let's use high-throughput computing to do that. And now we know what we're looking for. We're looking for a material that looks like this, that has a low Hall effective mass. I'll put a number, 1. Lower than 1, the mass of the electron. That's a reasonable limit. And then I want a band gap that's higher than 3 eV, okay, to be transparent. And let's not forget, we also want to be able to dope this material. It's not always trivial to dope it. But we know what we're looking for. So let's put, I'm sorry, maybe you don't see it very well here, but let's put the machinery of high-throughput computing together. And this is a tiered screening, again. So you should see a funnel. Sorry, the color is not very good. So the funnel starts with easy properties with Hall effective mass that will give you a sense of mobility. Then you get transparency. That's related to band gap. And at the end, we test dopability. This has been done on 6,000 known oxides when we started. Okay, so we took a database of ICSDs, a very large database of known oxides, and we started doing this screening. And for those who know something about ab initio computation, we play with different levels of theory. This is DFT. This is GW, gives you better band gaps. DFT is known to give you problems with band gaps. And this is actually a combination of different techniques for dopability. So we have to play with all the different tools to get different properties. Okay, let's look at the first step. What we did is develop a way to automatically compute thousands of band structures. And I think the database now has 30,000 band structures. When we started working, we had 6,000. And so for every material, we can put a band structure. Okay? We can connect a band structure to every material. And if you can connect a band structure, you can actually connect an effective mass to every material. A Hall effective mass and an electron effective mass. And you build a large database of those properties. So the first thing we did is we look at how do the electron effective mass compare to the Hall effective mass. Just look at the database. And this is the distribution of electron effective mass. And this is the distribution of Hall effective mass. And you already see from the data that it's very difficult to find a low Hall effective mass compared to find a low electron effective mass. The blue is much skewed towards smaller values. And this is this picture in action. This is, we're not totally surprised. It's nice to see it in the data. But still, we can find that the best n-type TCOs are here. So not much to optimize in terms of effective mass. We can find that the current p-types are here. And you can see that there are not many, but there are few materials that are doing better than the current p-type. And so this is going to be a focus now on this material that we can find totally by computational screening. Okay. So to give you an order of magnitude, we started with 6,000. If we do a reasonable cutoff on the value of the effective mass, and what we did is we looked at the known ones, and we said we want to do roughly 2 times better than the known ones, which is a reasonable thing to do. We actually start with 6,000, and we have only 20 compounds. And so I mentioned finding the needle in the haystack in my title. This is a really needle in the haystack problem. With these 20 compounds, we can do is use something actually better than DFT that's more accurate. 20 material is actually okay with coming with the big guns. And so this is what we did. On these 20 materials, we computed band gaps with a technique that I'm not going to go in detail, but that just gives you better band gaps. And then you can put all of that together, the computed effective mass, the computed band gap, and you can show all these red points are materials we found from the ICSD that have, by definition, lower whole effective mass than those current p-type materials. Okay? So this is a prediction. The materials we find to be interesting, purely driven by computation. And we put the n-type here, so this is an electron effective mass. Indium oxide, zinc oxide, tin oxide, to actually compare. And we see that some of them are getting really close to this n-type. So there's some hope you can find interesting material. Of course, I need to stress that we need always to worry about dopability. It's not like every oxide can be p-type dope, not at all. So at the end of all this computation, we do defect computation, lots of defect computation that are more expensive, and then some of the candidates actually are killed by dopability. So this is the tier screening approach. At the end, you do the most expensive thing, which is defects, and you remove some of the candidates. But let's focus on this sweet spot here, where we find materials that are p-type, and this should not be too much absorbing. There are high band gaps higher than 3 eV. And let's focus especially on one of them that we picked, which is bismuth tantalum oxide. And why this one? Because this one we actually worked with experimentalists to actually see what properties we could see. Why did the computer pick this material? Look at the curvature of this band. We're looking at low whole effective mass. We want curvy valence bands. And this is a very curvy valence band. We want a large band gap. That's what you see. And actually, the p-type dopability was OK. It was not great, and I'll get back to that, but it was OK. It is a perovskite structure. These are very common structures in oxides. And there's something magic about perovskites. For some reason, when I go to an experimentalist and ask to work on a new material, it's always a lot of work. So, people are reluctant. And then you tell them, OK, it's a perovskite, and then they say yes for some reason. So I cannot put that in a computer. I don't know why, but it's the way it is. So perovskites are fascinating structures. And you can see this crystal structure here. And so I work with mainly Gene Santovich from Cornell University, who actually made this material. This is a known material where the properties were known. So he made very good thin films and also powder of this material. This is the TEM of the material. And then we started looking at the properties. First thing to measure, the easiest, is transparency, and good. The prediction was right. This is transparent material. Okay? Then we look at electrical conductivity, and there was no electrical conductivity, but we had some sense that there were some dopants that you needed to put. And if you put some potassium on barium, in terms of doping, you actually can have a signal that's good enough to do whole measurements, and you can see mobilities. And the mobility we measure are around 38 centimeters squared volt second. This is not huge in the world of semiconductors, but in the world of p-type TCO, it is actually pretty high. These are the other p-type TCO that are around, let's say, up to 10, and this is where we are. So this is a very highly mobile material, and again, purely found by high-throughput computing, found in a database. What's the problem? There's always a problem at some point with materials. What's the problem with the material here? The problem, as far as we are concerned now, is the carrier concentration is still too low. So we're working on defect engineering to raise that number. This is too low for application, as far as I know. Okay? So we're trying to raise that number. But this is still a very interesting finding, because nobody would have thought bismuth would be a high-mobility p-type material. People work a lot on copper, for instance, and we're showing that bismuth-based chemistries are really interesting. So the bismuth here is what makes really this band curvy. This is the wave function, actually, from computation, where you see bismuth and oxygen. And this is the character of the wave function. This is because bismuth is hybridizing with oxygen that you get this curvy band and this high mobility. OK, so a fair question is, why do we stick with oxide? Oxide have flat valence bands. So you're trying the worst thing in the world to make a p-type TCO or p-type TCM. And they're all kind of very good reasons in oxides to work with oxide, including stability and processability. But what our study shows is very uphill battle. That we found 20 over 6,000 material. So what's nice with the data we have is that you can actually easily scale up things when you have an automation scheme. When you can run 6,000 oxides, it's only computational time to run more than oxides. And that's what we did. And now we have around 30,000 compounds, including all kinds of chemistries. And then you have data, so you can test certain things. And you can ask yourself, what's the distribution of Hall effective mass based on thousands of data points between oxides, sulfides, nitrides, and phosphides? And what you can learn is that in terms of Hall effective mass, I mean, there are other properties that are not as good, but in terms of Hall effective mass, you can get a much lower Hall effective mass in phosphides. And we've published a few things on that, and we're working in this field now. I don't really have much time to talk more about this, but this really shows you, interesting point here is to show that when you build it for oxides, it's not like an experimentalist, it's very difficult to switch chemistries. It's difficult to put an oxide in if you're working in a chamber with oxides, it's going to be difficult to put phosphides in there, okay? But for theorists, it is pretty easy, okay? Just changing the charge of your nuclei and the number of electrons, okay? Okay, so this is what I had to say about those two points. But one thing that I want to get back at is everything I did with the TCO was based on known materials, things that were in the inorganic crystal structure database. So it's a very interesting question to wonder, can we actually find for unknown materials? What about if the best TCO has never been seen? The chemistry has never been seen, and the crystal structure has never been seen. Okay? So we've been working on that problem, which is a very hard problem. And in this framework, we want to replace the database of potential materials to do high-throughput computing by maybe new materials. Okay? And how do we discover that? What we've been developing is tools to do that very quickly. And so these are based on machine learning combined with data. And so what I like to do is often take very simple ideas that come from experts in the field and give it a little bit of informatics or computer science twist. Okay? So if you talk with a material scientist or a solid-state chemist, there's some substitutions that would make sense. Let me explain. If you have calcium titanium oxide and you know it forms a perovskite, a good chemist would tell you, okay, you know it's likely that barium titanium oxide could be in the same crystal structure, barium calcium. They're similar. Sometimes it's based on things like the periodic table or ionic radius. Sometimes it's just based on experience. Okay? And so this type of substitution are really driving the way people make new materials. Can we actually learn that in a computer? That's really the idea. And I really want to make a general point on the use of machine learning. And this is one of the last things I saw that I found really amazing. This is actually skin cancer, and this is skin cancer, this is not skin cancer. As far as I'm concerned, I don't see the difference. But a medical doctor, a very well-trained medical doctor, years of training, can see the difference. And it's very, very important to be able to see the difference. What I was amazed to see is actually machine learned models actually built to do that process of detection of cancers. And how does that work? They have database of cancer and non-cancer. They train on this database a machine learned model, and then they can make predictions. Okay? And so in this paper, they say that the model is doing as well as the expert. And that's from 2017. Recently, I was searching on Google. They're actually starting to say that you're doing better than the expert, okay? Which is pretty amazing. So this gives you the context of the importance of the machine learning methods. Can we use these machine learning methods to actually find ionic substitution? A little bit like the skin cancer problem. And so can we replace that process where data has been seen by material scientists and solid-state chemists, and empirical rules are also built, but they're often qualitative, okay? And then predictions are made. Can we replace that by a machine learning model? Okay? And so this is what we try to do. The first thing you try to do is to build a probability function. That's one way of addressing the problem. And this is a probability function of substitution. So I want a big function that says, if I have a few ions and a few ions there, what is the chance that I can substitute? And I can have more than one substitution, which is actually something very neat and more difficult for human beings. Okay? You can have more than one substitution. And I want to assess how likely is this. If I have a probability, I can assess that. Okay? Next step, you have a probability. You have to express it in a certain mathematical way, the probability. There are different ways to do that, always different ways in machine learning. This is the way we took the approach. So we have some binary features that are basically have a weight, lambda. So every pair of ions has a weight, and that's how likely it is to substitute to each other. Barium and calcium, barium 2 plus and calcium 2 plus, that is going to have a lambda that's very high if you train it on data. Okay? And the training process is to find this lambda, basically. And as soon as you've trained, you have a big probability function, and you can ask whatever questions. If I have calcium, titanium, and oxygen, can I have barium, titanium, and oxygen? This is one of the results you get. This is those lambdas. These are the weights between a list of different ions. They're grouped along the periodic table. Okay? So red is very likely to substitute. Blue is unlikely. And actually, you see the periodicity of the periodic table coming, which makes sense. Okay? And what's very nice is that you can also compare to ionic radius and things like that, but it combines all these rules together in a probabilistic function. And then you have a way to actually search for new material. Let's say I'm interested in one chemistry, barium, titanium, and oxygen. I use my machine learned model. I find suggestions of substitutions. Something very important that's sometimes misunderstood, I also use DFT to do a step of stability. Basically, I looked if the energy of the compound is very, very high. So that gives me a second way of actually lowering the number of candidates. And then if you do that, you actually come with new compounds that you suggest. This compound should form in that crystal structure at this chemistry. And what's pretty amazing is that it works. All these examples are examples of materials that were predicted by this method and were made experimentally and have never been made. So this is truly synthesis that's driven by a computer. So it's pretty, I mean, you see there's a lot of lithium and sodium in there because we did a lot of that. We're looking for better cathode materials for batteries. That's why you have this bias. But you can use this method for other things. And I want to talk about the more recent work that I'm actually not involved with, but use the technique. And this is from Shui-Ping Ong from UCSD, and he found a better phosphor material through this technique. What are phosphors? Phosphors are materials that transform certain wavelength of light to another wavelength of light. And this is really important if you work with LEDs and you want to actually have white light from an LED. Let's say you have blue LED and you want white light. So it's very important, those phosphors. And so what Shui-Ping Ong did is he used our substitution algorithm to find this new strontium lithium aluminum oxide material. Nobody had ever made that material. They actually made it, and it was actually an excellent phosphor. So this is beautiful work from Shui. And actually they had a nice sentence saying this is clearly a non-trivial crystal prediction that cannot be easily replicated using traditional chemical intuition. And I read that and I really loved it. I also want to point out that this is because those tools are available open source, that Shui-Ping could use my code, basically, or my method very easily to do predictions. So it's very important to share codes. And this gives a very nice transition to sharing code is important. And I would argue that sharing data is also very, very important. And let me finish by, in an ideal world, how would you like to design the best material for an application? Let's say you're starting your PhD and you want to work on solar absorber and you want to put some new transparent conducting material in your solar absorber to make a solar cell. How do you pick which material you're going to spend 4, 5, 6 years of your life on? And I see a lot of very young face here, and our intuition would be to say, okay, let's Google it. Okay. Can we actually look for materials that have all these properties, band gaps, effective mass, maybe another property more related to your application like work function? And we actually cannot do that, but it's crazy. We can find flights, we can find hotels, we can find everything on Google. Why can we not find materials? And I would argue this is because we know nothing. There are around 50,000 to 100,000 known inorganic compounds. You can discuss about that number, but this gives you an order of magnitude. On many of them do we know fundamental properties like band gap, dielectric constant, elastic constant? I would argue maybe a few hundred. Okay? So we know very, very few about all the possibilities that exist. And I talked at length, about high-throughput computing, so we can compute properties of materials on a large scale now. And so I'm part of a project called the Materials Project, where the idea is to become somehow the Google of materials properties, of computed materials property, okay, that you can use to ask those questions. And so this is a free and open website and a database, actually. And the best, I'm not going to talk much about it, but what I would say is the best thing is to just look on the website. Look at it, see if anything is interesting. There are a lot of data, and it's growing. You have band structures. You have all these effective mass that are coming. You have energy, space diagram. We have around 60,000 users now. This is total number of users. So it's really something growing. And it's very collaborative because it brings, a lot of expertise, including people from computer science and including specific experts in specific material properties. And this is really growing. One of the things we've been working on lately is to bring vibrational properties, phonon band structure. So this, I've talked about electron band structure. It's the same. You can make a band structure in reciprocal space of phonons, of vibrations. These are more expensive computation, but we recently developed an automation of them. And so we're building a bigger and bigger database on that. And this brings a lot of very exciting opportunities. Okay, on this I'll conclude. I hope I'll give you the feeling that ab initio techniques are becoming really a tool that can go from understanding. Traditionally it was more understanding, but now it's really coming to predictions. High throughput computing is a really good way, an efficient way to actually search in certain applications for interesting materials. I give some example of in the field of TCO. And then there's a very fascinating work, and this is an ongoing project. There's still problems with this method, and we're working on improving it, combining machine learning and DFT to find new compounds, where we've shown some success where we can synthesize this material. And public sharing of data is really important. When you think about transparent conducting oxide, effective mass are not only useful there. They could be useful if you're building a solar absorber. But maybe I don't work on solar absorber, but I can share this data so somebody working on solar absorber can use it. And this is really, really important. So this, you can have more info on my website, and also please feel free to shoot me an email at any time when I'm talking to me after the talk. I need to acknowledge a lot of people. I realize I might have missed people. This is people from my group. Some of them are really involved in all this work. All collaborators from my university in Belgium, but also from all around the world. And funding, public funding, but also, and I really want to acknowledge that funding from industry, they're actually starting to realize that ab initio computational tool, including high throughput computational tool, can be very useful for industrial application. Thank you very much.
We have time for a number of questions.
Very exciting talk. I have a question about TCOs and action prediction. I think the effective mass is definitely a very important first step, but for most of the semiconductor materials used for TCOs, liquidity is really not limited to fundamental phonon scattering. It's actually used defects. So how well can the model deal with defect scattering now? Characterize the materials more out to defect scattering like that.
So we're taking, actually, the first step we're taking now, as we speak. I didn't have time to talk about it, but it's actually to model the electron phonon scattering. That's somehow I think it's also the most intrinsic property. Yeah. You're always going to have vibration in phonons. You're not going to get rid of that. And still, we see large variation. For instance, the boron phosphide there, that's actually has a huge mobility, has a very weak electron phonon scattering. And it's very difficult to predict somehow, to look at it. And so we found that this is the case. I didn't talk about it. This is an unpublished result. Okay. So we started computing, because we involved in phonon computations, high throughput phonons. You also actually get electron phonon coupling for free. So we're actually working on bringing that into the mix. But then, of course, then you need to go further. And you need to look at defects scattering. There are some models that that you can work on. I haven't really looked in details, but there are some models that exist, and also grain boundaries. But that's I would say, that's the future work.
Great.
Yeah, this is a very good point. So the assumption we make in this work is it's an assumption actually very often made in semiconductor or fields like thermoelectrics where you look at doping of material. It's the rigid band, what's called the rigid band approximation. So you assume you don't put too much impurities that you're not perturbing dramatically your band structure. That the only thing you do when you put the impurity is to move the Fermi level. And this is a reasonable assumption in semiconductors if you don't push it too hard in terms of amount of impurities. But indeed, as the question is about the future and next steps, that might be an interesting next step. Is to say, what about the taking that effect into account?
Does your very fundamental work give a preview about toxicity of materials? The more useful material, the more there will be, the more will end up in our environment.
That's a very good question also. Although, I mean, the issue with that I personally, I'm not an expert in toxicity. I haven't had a chance to work yet in collaboration with somebody who could teach me about toxicity. And I think that's, so far, I haven't put, I mean, you see some of these things are really bad. I mean, like, I'm showing some of the compound, the worst we see some thallium compounds coming. Thallium-based materials that just come from the screening because they have very good properties. But indeed, what we do is we know that. This is a very simple thing. You know this is very toxic, so you don't even want to consider it. But I think we can do more subtle things with these databases. Yes.
On machine learning method, I'm just wondering how you know to what extent the predictions are good.
So when you build I mean, I haven't had a chance to talk about that, but when you build a machine learning model, you always do some kind of cross-validation at some point. And that's really, really important. And I would argue that if you ever see, especially a system with a lot of parameters, so if you have a very complex model with a lot of parameters and you don't see much of cross-validation, that's a bad sign. Okay, so how does cross-validation work? Cross-validation is a way to test your model, and especially to test if you're not overfitting. So if I have a model with thousands of parameters, I can always fit very well to my data. Always. So what you do in cross-validation, you kind of prevent for that because you say, okay, I'm going to take my data and I'm going to remove 10% of my data. And that's my test set. And I'm going to train on the 90% of the data that's left. And I'm going to see how good I am to predict data that I haven't used to train. And that's really, really important. And you can do this type of cross-validation, and this gives you a quantitative sense of how predictive your method is. And every time we develop a machine learning model, we do that at some point.
So you've been talking about compounds. So how well does this work for metallic alloys? If we do ionic alloys, I know people are doing stuff like this, but then you try to get mechanical properties or maybe magnetic properties.
Yeah, so in terms of, so for alloys, there's nothing that prevents to use the method to study alloys. And we have a project actually on high entropy alloys where we do this type of high throughput screening methods. But we focus more on stability and formation of alloys, where, there the atomistic level works quite well. And this comes to my comment on relevance. If you look at mechanical properties, on the other hand, you need to be very careful about what you can compute at the atomistic level. That being said, what I'm learning more and more, there are some indicators, for instance, stacking fault energies, that you can get from the atomistic level that can be useful indicators for mechanical properties also. And I think there's also an interesting avenue where you actually combine this data that you get, elastic constant, maybe stacking fault energy, and so on, and then you build them into higher order models. But I'm not an expert in higher order models or multi-scale, but I think there would be a nice collaboration maybe with people working on multi-scale.